of Aluminum Trade Association magazine, and it claims that friction stir welding of the fuselage of a new private jet is significantly reducing the cost because you don't have to have heavy flanges, you don't have to drill rivet holes and things like that. For example, when you rivet things together, I can't remember, I had a student work at Boeing once in the door product center where they build aircraft doors for jet aircraft, and each rivet hole gets drilled by hand about 4 times or 5 times. You first drill the hole sub-size, and then you drill it with the size drill that you want. And the reason you do that is there's less chatter and you get a cleaner hole if you drill it first with a small drill, and then the second drill is only taking off a little bit, and so you don't get as much vibration and chattering. And then they drill it with a ream, and then there was another reason why they drilled it a 4th time. I can't remember. But that's all a hand operation. And also in that situation, I remember going through the plant and saying, well, how much does a door cost? And they frankly didn't know, because they don't generally just sell doors. I mean, they kind of sell airplanes, right? But it was kind of an interesting operation because it's a very deterministic manufacturing process. It takes about 3 years to build the aircraft, 2 or 3 years to build the aircraft. It only takes about 1 year to build a set of doors. And so therefore they know exactly how many doors they're going to need, because it kind of goes into a bigger component. But they really didn't have any idea what it cost. And so I basically said, well, they made little doors like the escape doors, you know, if you're in the escape aisle. They made regular walk-in doors, and they made great big doors that were half as wide as the front of this room, which were the big freight door. Actually, they might have been almost as wide as the front of this room, which are great big freight doors for the freighters. But I was still curious because the student was going to be doing a thesis on cost reduction and stuff, and I wanted to get some sort of feel for what the value of a door was. So I asked them, well, how many doors do you build in a year? And they said about 750. They at least knew how many they built, right? And then I said, well, how many people work here? And they said 250. And I said, okay, it costs you $50,000 for a door. And they looked at me and said, well, why do you say that? And I said, because in a typical manufacturing operation, the value of the output of the product per employee is about $150,000 a year. And you can go across a bunch of industries. Some industries it might be 100,000, some it might be 200,000, but I've never seen any industry, well, I take that back. The gold industry is a little different where the value of the material. But for most common manufacturing industries, the value of the product sold is about $150,000 per employee per year. And if you make 750 doors with 250 employees, that's $50,000 a door. So whenever I walk through an airplane door, I think, well, that's the $50,000 door, even though they didn't know what it cost. Actually, one person tried to give me an estimate. He says, well, maybe 14,000. There's no way that door costs 14,000. I'm sure it was closer to 50. Then I talked to one of the managers, and he says, well, that might be, I told him how I figured it out. I said, well, that might be about right. But if you just think about it, how can you afford to pay the employees unless you're selling, you know, $150,000 of product per employee? Of course, they could have been losing their shirts on it and not know it, the way the accounting goes in some companies. Then I could do a slide on accounting, but I won't right now. Soldering fluxes must have, we were talking about soldering, must have chemical activity. They've got to clean the oxides off the surface so that the material can wet, which is called wet spreading activity or wetting power. Thermal stability, it's got to be able to stay there during the whole process and continue to protect things and be non-corrosive. Solderability of a clean copper surface degrades rapidly after cleaning. If you're using a RWMA flux, or not RWMA, RMA flux, for whatever reason, I can't remember the reason, Oh wait, I do remember. Reactive, mildly active, I can't remember. It's mildly activated. Flux will have some chlorine in it. And our flux is basically just rosin. In fact, I guess that's what the R stands for. Rosin mildly activated has got a little bit of chlorine in it. And there may be a couple of different levels of RMA fluxes with different amounts of chlorine. And we mentioned that a lot of electronics will not allow any chlorides in the fluxes, which means that you've really got to essentially clean your copper surface within less than an hour before you go ahead and try to solder it, because the rosin flux doesn't work all that great. It works great for the spreading activity, but the chemical dissolution is not quite so good. Anybody know what the other main use of rosin is? What? Sorry? Anybody grow up in the South? Rosin baked potatoes. You have a big pot of pine sap. You take a baked potato, wrap it in aluminum foil, and drop it in this. You put the whole thing on your grill and melt the rosin, and you bake your potato. It comes out perfect. Don't ask me why, but it comes out perfect. So anyway, you just never grew up in the South, huh? And the thing is, you got to wrap it well with aluminum foil. Otherwise, it gets kind of a pitchy taste. But otherwise. So removing oxides, there are several ways to do it. One's chemical dissolution. The acetic acid basically dissolves copper oxide. The chemical reduction, where you use hydrogen. Hydrogen gas will reduce oxides to form water vapor, but you've got to have dry hydrogen gas. I don't know if I've got a plot of that right now, but hydrogen in theory can reduce almost any oxide if it's dry enough. It doesn't have any moisture in it. Chlorides tend to react and form the chloride, which dissolves in the flux. And there's also something which has the unfortunate name of reaction flux, because these actually are more of a reaction, or just as much of a reaction as this one. But for aluminum, people have developed what they call a reaction flux. There's certain types of metals that cannot be soldered. Titanium is one. Tantalum is another, niobium is another. A lot of the refractory metals, zirconium, cannot be soldered. And sometimes people will list aluminum as one of the materials that can't be soldered, because if you try to use a chloride flux on aluminum, or most chloride fluxes, it just won't work. And that's because most chloride fluxes are things for soldering are zinc chloride in water. And it might be a 5 or 10% solution of zinc chloride in water. And that works fine for cleaning copper oxide, but it will not clean aluminum oxide, because aluminum oxide melts at 2,000 degrees centigrade. It's extremely stable. What happens if you use pure zinc chloride or tin chloride, or a mixture of the two, you can get down to fairly low temperatures, like 400 degrees centigrade or so. Not 400 centigrade, but 400 degrees Fahrenheit, 400 to 500 degrees Fahrenheit. And what happens is this reaction, if you have tin chloride plus aluminum, will form aluminum trichloride plus tin metal. Essentially, you're going to reduce the tin chloride with aluminum metal. Here's your aluminum oxide on the surface, and I've shown it broken up. Ordinarily, it starts out as a continuous film, and it may be 100 angstroms thick. It doesn't have to be very thick to be very protective. But as you heat things up, some little cracks will form, and if this whole thing is covered with this molten chloride, the molten chloride will seep down through some of the grain boundaries, form little cracks. It will get down to the aluminum underneath the oxide. It will react with it to form aluminum trichloride gas. Well, actually, it is a gas at these temperatures. And tin. And then what happens is the tin undermines the aluminum oxide and floats it away, like icebergs being, floating away in the ocean or something. And you basically don't decompose the aluminum oxide. It's too stable, but you actually lift it off on a little layer of tin. So you've now pre-tinned the aluminum underneath, and you can solder to it. You have to usually often have a little bit of brushing action or abrasive action to help scrub these little bricks of aluminum oxide away. but you have this reaction. Now the problem is aluminum trichloride is a very reactive gas. If it sees any moisture, it reacts with the water to form hydrochloric acid and aluminum aluminum oxide again, and hydrogen gas. I remember once I wasn't thinking, one of my children had a science fair project, and they wanted to look at solubility of different materials, so I went to the lab and I got a bunch of chemicals and I brought some home. You're doing different chlorides and doing solubility, and so I dumped, not a whole lot, it's like 1/8 of a teaspoon of aluminum chloride in water, and the whole thing caught on fire right on the kitchen table. That was pretty exciting for my son. But in any case, I decided maybe we should be more careful when we add aluminum chloride to water. Yep.
Don't you just sand aluminum in the solder?
Nope. The aluminum oxide reforms. Remember, the Langmuir is 10 to the -8 atmosphere seconds. And a layer of 25 angstroms to 50 angstroms of aluminum oxide will regrow within a fraction of a second. If there's any moisture around, then this reaction will not go. And remember, I said that the typical soldering flux might be zinc chloride, but it's dissolved in water. This has to be an anhydrous salt of tin chloride or zinc chloride. If there's even 1% moisture around, that will essentially degrade this such that it essentially won't work, because the aluminum trichloride will just reform the aluminum oxide that was there before. In fact, the biggest problem with these fluxes is they're hygroscopic. It turns out, unfortunately, these chlorides are not only hygroscopic, they're deliquescent. Anybody know what deliquescent means? It's big time hygroscopic. Hygroscopic is something that absorbs moisture. Well, something's deliquescent, not just absorbs moisture, it absorbs moisture. If you took lithium chloride is one of the most deliquescent chlorides. If you took a small grain of lithium chloride, smaller than a salt crystal, put that one crystal on this table in this room and came back an hour later, you'd have a drop of water there the size of a pea, okay? Because it absorbs the moisture from the air, and it forms a surface layer that keeps on absorbing moisture. It does not take very much of these materials to absorb a lot of moisture. So frankly, I've only run across, I did aluminum soldering myself once, but I did it in a blind geometry where I could not get rid of the flux afterwards. I was making actually a demonstration for a class, and it worked just fine for a year. The second year I went to it, and I picked it up, the whole thing fell apart in my hands because the moisture had been attacking it, and it was corrosive. I couldn't remove the flux from the inside of this thing, and over time the moisture had gotten into some of the other holes and corroded the whole thing, so it fell apart in my hands. So the next time I made it out of steel and welded it, and it didn't fall apart, except it weighed 10 times as much. In any case, that was one time I was familiar with this. Another time, the only time I've ever had anyone industrially call me on soldering of aluminum was some people in Florida. They said, well, these people advertise that you can solder aluminum. We've been trying to do it. We're having a terrible time. I said, where are you located? They said, in Florida. I said, of course you're having a terrible time. It's because it's humid in Florida. And just the humidity in the air means that flux probably, once you take it out of its container, probably will last for about 1 hour before it just picks up enough moisture from the air to degrade it. So anyway, there's various ways to clean the surface. Another thing to be concerned about is how well something wets the surface, what type of fillet it forms. This is out of this book by Klein Wasink, Soldering Electronics. I'll pass it around. If you want to know anything about soldering, it's in this book. There's lots of books on soldering, but this is definitely the most comprehensive. That essentially is Philips Laboratory in the Netherlands, which makes, they were the inventors of compact disc players and things like that. That's basically their handbook that they ended up writing on soldering, but it's by far the best thing I've ever come across. What they're looking at here, these are through wires on printed circuit boards, and people were looking at how much solder do you need to make a good joint. Turns out the best joint is one that has a reasonable fillet rather than a great big hump or too little. You want to form a nice symmetric fillet. You don't want a great big hump where the solder bows out this way, and you don't want a very small fillet because there'll be too much stress on the solder so far as that goes. There's something called the bond number, which is the ratio, forget that, that's an old, I knew there was a reason why I did this. The bond number is the gravitational force divided by the surface tension force. It's a dimensionless number. So if I got a force divided by a force, it's dimensionless. How many people are familiar with the dimensionless numbers from somewhere in your previous engineering? Okay. Pardon me? Current engineering? Okay, well, good. Dimensionless numbers can be very, very useful for doing rough estimations of things. And we'll use some more. But the bond number in this, well, any set of dimensionless numbers, you can have an energy divided by an energy, a force divided by a force, a viscosity divided by a viscosity. There's various ways to form dimensionless numbers. And actually, they basically come out of the basic differential equations that describe the physical processes. I had a student, a doctoral student a few years ago, work out a new way of looking at differential equations so that basically the dimensionless numbers pop out naturally out of those equations. Even if you don't know what the dimensionless number should be, there are ways to mathematically generate them. In any case, the bond number has nothing to do with bonding. It just happens to be, usually these things are named after people, like the Reynolds number or the Grashof number or the Prandtl number. Anyway, the bond number, I assume, was named after Mr. Bond, whoever he is. It's probably not James Bond. But in any case, the gravitational pressure for a sphere of a liquid sitting on top of a substrate, if the sphere is radius r and has height h, the gravitational pressure top to bottom is rho gh. The surface tension pressure for a sphere is 2 gamma over r. And if r is on the order of h over 2, it is equal to that for this geometry, but for a fillet, it's going to be something like this. But the bond number is rho gr squared over gamma, which means that the bond number varies as the square of the radius. So if I go back to these types of little solder balls or whatever, and I want to know what will form a nice symmetric shape, and this thing is worth okay for this, to show these shapes up here. I want to get a nice symmetric shape. I can go to the bond number. If I want a symmetric shape, I've got to have something where the size or the whole thing is dominated by surface tension forces rather than gravity forces. And if I run through typical values of density of lead tin solder, gravity is a constant, and gamma, and say I want to know when the bond number is equal to 1, so I'll set the two of them equal, and solve for r squared, I will get an r value on the order of, let's say, about 2 millimeters. And that means that something that's 1/8 of an inch in size, an eighth of an inch is 3 millimeters. If the r is 2 millimeters, well, whether it's an eighth of an inch or 4 millimeters, 3/16 of an inch, it doesn't matter. Something on this order of size of 1/8 of an inch is going to give me a solder ball where gravity forces are equal to surface tension forces. If they're equal, I'm going to see some slumping, and that solder ball is not going to have a completely spherical shape because gravity forces are equal to surface tension forces. However, if I wanted something where the gravitational forces are 1/10, then I have to have something that's only 3 times smaller than that. So if I had something that's 1 millimeter in size rather than 3 millimeters in size, I'll have a nice sphere. Now, the U.S. Army needed to know that and could have saved themselves a lot of heartache back in the Civil War. Right now you can go to Arsenal Mall in Watertown, which was, when I was a student, it actually was part of the Watertown Arsenal, which had been there since the 1820s or whatever. And the arsenals are where the U.S. government, the military, had their own manufacturing facilities, and they used to make things. And one of the things they wanted to make at the Arsenal Mall back in the Civil War is they wanted a cheaper way to make cannonballs. And so they had ways to melt the cast iron, make the cannonballs, but they wanted them nice and spherical. And so they thought they could do this in a drop tower. Okay? Now, you probably could do this in a drop tower if the drop tower was located in outer space where there was no gravity. Or actually, you can do it in a drop tower because there is no gravity in a drop tower as it's dropping. And so it'll just be held together by surface tension forces. But they didn't understand in the 1860s very much about heat transfer. And a cannonball that's this big around takes a while to solidify. And you'd have to have your drop time be at least, let's say, 2 times greater than the solidification time, which means you have to probably drop it from 100 miles up or something like that. So they weren't able to make cannonballs. They all came out, they made a lot of splats, okay, splatted cannonballs. And they also tried to make smaller musket balls and things. Well, they didn't work very well either because those were typically a 1/4 inch in diameter, and they didn't get very spherical balls. However, there are applications for doing this. As a young assistant professor, some person came to me and said he wanted to make some ruthenium balls. And I said, what do you need ruthenium for? Ruthenium is platinum group metal. Well, it turns out the inks in ballpoint pens, or not just ballpoint pens, but the fancy ink pens, these inks tend to have chlorides and be fairly corrosive. And if you're paying $50 or $100 for a fancy ink pen, you don't want the nib at the end has a little platinum ball, has a little ball on the end to wear out, because then, even if it's a year later and it wears out, people think, well, I paid $50 for this pen that wore out in a year. And the inks are fairly corrosive with these chlorides. The platinum group metals are very corrosion resistant, and for whatever reason, this person had determined ruthenium would be the best. The problem with ruthenium is you can't buy it in wire form. If I want to make a little platinum ball, nice and small, I just buy some wire, draw the platinum wire, I chop it up into cylinders, and I put it between 2 plates and just roll around like that and grind it into balls, and you get very, very smooth balls. That's the way we make ball bearings. And you can make fairly large ball bearings by just chopping up cylinders of wire. Except he couldn't buy ruthenium wire, and the reason you can't buy the ruthenium wire is because of its crystal structure. It happens to be hexagonal close packed. Platinum you can buy because it's face-centered cubic, but hexagonal close packed crystals don't deform in a nice uniform way, and so you can't draw the wire. All he could buy was ruthenium powder. And he says, he came to MIT and he said, it turns out a lot of the ball bearing industry in the United States is situated in Connecticut, or was. He says, can you make ruthenium balls? I've got some ruthenium powder. I said, sure, I can probably do that. So I went across the hall to the same electron beam melter that I made my wife's engagement ring on, which was actually sort of an interesting machine. It was one of the last machines to kill someone at MIT. That was before my time, but it was about 40 years ago. And this was an old Korean War power supply, radar power supply. And the guy who was operating it about 1960 or so, he was working on Christmas Eve. And the thing used to make some unusual noises, like zap, every now and then. And he used to just kind of grab this wire and pull it away when it would start to arc. And he did that one Christmas Eve when it had been raining out and his feet were wet, and he ended up electrocuting himself. Nonetheless, I didn't always tell my wife. I think it's a few years after we were married, I told my wife the story about the machine was the one that someone got killed on. And I really didn't tell her until about 20 years after we were married that the whole time I was doing this, as I was sitting there melting this little ring, and I had to go back several times to do it for reasons I won't go into, I would hear this zap. And I'd turn the machine down and I'd look around and I couldn't find that short anywhere. course, I wasn't grabbing wires and just pulling them away. This is, 7,000 volt wires that this guy was pulling, so it wasn't the brightest thing for him to do. In any case, finally, after about a month, I unscrewed one of these connectors, these military type connectors, and sure enough, inside there's a little carbon track in between, and so every now and then the thing would zap. But my wife wasn't she wasn't very happy when I told her that I'd done this for a month, right before we got married. But in any case, so I go across to this electron beam, and I take a piece of copper, and I take a ball bearing, and I just hit it with a hammer to make a little cavity, not a deep cavity, just enough to put the powder in, and put some of the powder in there, put it in the electron beam, and I melted the powder, and it immediately made about a 1 millimeter, nearly spherical ball of ruthenium. All you had to do was melt it together, the powders together, and they will naturally form spheres because of the bond number here. Okay, the surface tension forces are greater than the gravitational forces in most metals if you're smaller than about 1/8 of an inch in size, and they will naturally form spheres, very, very uniform spheres. So the guy was delighted. I gave him 1 or 2 balls, and I said, fine. And he started, I was about ready to, I thought I was done. He says, well, can you make 10,000 of them? I said, what? And, it took about 15 minutes to pump down the vacuum chamber and everything, and maybe I could make, so I said, well, we can try that. So I made up a little grid with 100 little things on it. And I tried melting it, and yeah, I could get about 50 good ones out of every batch, but it took about a half an hour to do it. I thought, this is not the way to do it. So I went downstairs here to the weld lab, and I took my little copper block, and I put it there, and I just took a gas tungsten arc welding machine, and I just went over the powder, and I could make about 70 or 80 good ones that way. So I gave it to a graduate student. He made 10,000 of them for this guy. I don't know what happened to the ruthenium balls, but surface tension does cause things to ball up. And then, well, I won't tell you. I did actually build a drop tower for iridium balls a few years later, but actually, I will tell you that story. Draper Lab over here makes a lot of very sensitive gyros for inertial guidance, and put them in aircraft so that the pilot knows what the orientation of the plane is and stuff. And for some reason, they wanted iridium balls 10,000ths of an inch in diameter. And they could buy them from Engelhard, the largest manufacturer of platinum group metals in the world. But Engelhard was charging $1 a piece for these things. Now, the metal content in these things was like 2 cents. And Engelhard was basically drawing iridium wire, chopping it up, grinding them down, and making little spherical balls. And they were making a fortune off this. And the problem was that Draper needed 1 million of these things. And at $1 a piece, that starts to run into some real money. So they said, can you make them cheaper? I said, sure, we'll just build a little drop tower. The only problem is iridium melts at about 3,000 degrees centigrade, so the drop tower has to be pretty hot. So, and you have to do it in a vacuum. Fortunately, for a 10 mil ball, it's not like the Army trying to drop cannonballs down there. It only had, I calculated, it had to be like a 2-inch drop zone. So I needed a 3,400 degrees centigrade furnace, about a tube, about 4 or 5 inches long. Ought to be enough safety factor to make these things, and just drop a little piece of one of these little rectangular wire or cylindrical wire pieces, just drop it through there. It should melt and turn into a perfect sphere. And hopefully, if I had another 4 or 5 inches in a cool zone beneath it, then I'd just collect the solid balls at the bottom. And that would be a nice, cheap way to do it. So, how do you build a furnace at 3,400 degrees centigrade? Same way Thomas Edison did it. A light bulb operates at about 3,000 centigrade. It's just a piece of resistively heated something. And remember, one of the first things that Edison used that was successful was horsehair. He found that the filament he finally came up with tungsten, but his first few filaments were nothing more than horsehair, and he would heat them up slowly, burn off the organics, and end up with a piece of carbon, graphite, and carbon melts at very high temperatures. So we just took a carbon tube, and we had to put some big current leads on it, and we just turned into a great big carbon tube light bulb that we resistively heated with about, I think it was about 1,000 or 2,000 amps. And we ended up with our light bulb, but a very special light bulb inside a vacuum chamber that we could drop this iridium. And we actually were able to melt a couple of pieces of iridium and turn them into spheres to show Draper Lab how they could go into production. However, Engelhard then found out that we could now produce these things for about 10 cents a piece, and so they dropped their price to about 50 cents a piece. And Draper decided they just buy them at that price rather than go into production. So it does help sometimes to have a technology when someone is gouging you, to develop a technology that can compete with them, whether you want to compete with them or not, just to get them to be more reasonable in their pricing. Any questions on any of this? Let's just finish up. If not, let me finish up soldering by talking about how do you test for solderability. And you should have a copy of this somewhere in your notes. There are a number of different types of tests for solderability. The first one up here, the automated dip test sample, I've kind of mentioned before, and part of this is cut off a little bit, but it's nothing more than a little lever arm, and you have a pot of solder and you put some flux on top of it, so you have a pot of molten solder, and you take a copper wire and you dip it in for a second or two, and you pull it out and you say, does it have any solder on it now? Okay, this is a pretty sophisticated test. You just stick it in. This is right. So it's called the and then they actually automate it so that you don't have to time the 1 second yourself. They actually have a machine that does it, and so you can control the time more precisely. It's called the automated dip test machine. Then they have another machine when you have a printed circuit board. Let's say this was a printed circuit board, and essentially you put this printed circuit board on a lever arm, and you swing it across a solder bath. This is akin to wave soldering. Remember wave soldering? You have this little weir, and you kind of pump solder up over that, and you have some foam flux. Well, since you're not just trying to do a single wire, you're actually trying to look at a whole circuit board. They have this little thing that automatically just sweeps it across there, and you can change the speed of the thing, and you look at it and say, did I get good solder joints or not? That's another sophisticated technique. Another one is you basically take a little mandrel, and you put the wire in it with a little bead of solder, and you heat the whole thing up, and you see if it solders the wire to the mandrel. That's pretty sophisticated. The last one, and you can buy a machine that will do this for only $50,000, okay? And the machine is worth at least $5,000, okay? But they don't sell a lot of them, so they charge you $50,000. But it's basically the automated dip test, but it's instrumented so that you basically push the wire into the solder bath, and you weigh the wire at the same time. And you get a plot that looks something like this. When the wire first goes into the solder, the force on the wire decreases. And the reason it does, this is the little piece of copper or whatever you want to test. When you first start pushing it in, it's being pushed. It's not wetting because the solder hasn't wetted the copper yet. The reaction hasn't occurred in that first fraction of a second. And you're actually pushing down. The copper is less dense than the lead tin. The copper should just float on top of the lead tin. If you try to push it beneath the surface, you have to apply a force to get it to go beneath the surface because of the contact. So the thing first goes negative as you're pushing it down in, and then it starts to wet, and I have a zero contact angle, and then it completely wets, and now the solder wetting angle is trying to pull the wire in, and so the force goes positive. It means it's pulling now I've wetted, and so this time in here is the time it takes to actually get wetting. And you go in, you find out what the height here is going to be proportional to the contact angle here, the amount of force that's pulling down with. And then when you pull it out, you'll find a little blip as you change the contact angle as it's finally coming out. And then when it comes out completely, they've actually got it wrong here. This thing should end up having a little bit higher value. Why should it have a little bit? Why should it weigh more when it comes out? Because it's got solder on it. Okay, it doesn't go back to zero. Is the point. So this is just a fancy version of this stuff up here. I guess the point here is solderability tests are not very sophisticated types of tests. It either works or it doesn't work, and you just try it out and see what happens. And that the final one, that last one, they do sell commercially a $50,000 machine to do this, and it's not terribly sophisticated, but it does give you a plot, and it gives you all kinds of numbers off that plot that you can do whatever you want with, try to make some sort of sense out of them. Finally, one of the things a lot of times people figure, well, it's just solder, it doesn't really matter too much what the composition of the solder is, and they run into a lot of problems with that kind of attitude. They figure the solder is not important. It turns out the purity of the solder is sort of critical. It turns out if you have aluminum, magnesium, or zinc impurities, you've got to be below 50 parts per million, or else you're going to find intermetallics that cause the solder to be kind of gritty. I remember people were trying to get away from lead tin solders, and I was at a conference in Honolulu a few years ago, and someone was presenting a paper on a lead-free solder, and they talked about the wetting angle and spreadability and everything, and I can't remember, it was a bismuth-based system, and I didn't ask them the key question on bismuth, but as a replacement for solders, lead tin solders. But I can't remember what else he had in there. I think he had cadmium. I think it was bismuth cadmium. And cadmium happens to be toxic in itself, but soldering is a low enough temperature, you don't have to worry too much about it. But it turns out, was it cadmium? Yeah. And he had some tin in there. And I said something about, I raised my hand in the question and answer. I said, well, did you check on the grittiness of the solder? He said, oh, well, that wasn't part of our evaluation. I said, well, was it gritty? He said, yeah, it is sort of gritty. And it turns out solder doesn't flow real well if it's gritty. And what happens is if you get these intermetallics, I don't remember what it was, but I knew that whatever his chemistry was, it had to be forming intermetallics. If it gets gritty, you now have a solid liquid mixture, and it doesn't flow as well. And so his thing was sort of doomed from the beginning. Anyway, so aluminum, magnesium, and zinc are bad, and only 50 parts per million. That's a pretty pure type of material. Antimony is put in at about 0.3%. In theory, well, it does several things. One is it helps with the fluxing, in that antimony will actually reduce copper oxide itself, and so it actually acts as a fluxing agent in itself. But in addition, people think they put it in there to reduce tin pest. Now, tin pest is a phenomena where tin exists in two crystallographic forms. One's white tin, which is what you're familiar with, and the other's gray tin. If you get down to minus 18 degrees centigrade, which is a little bit below 0 degrees Fahrenheit, it turns out that tin will transform from the white tin, which is body-centered tetragonal, to triclinic gray tin. And when it does that, it basically turns itself into a powder and decomposes. So people have done tin soldering in the past and used it at low temperatures in a cryogenic application. When they bring it out, there is no solder left because the tin itself just turned into a powder. Turns out antimony, small amounts of antimony, will inhibit that phase transformation. There's a story in the Russian winter of 1944. The Soviets had a stockpile of tin outdoors somewhere out beyond Moscow, And if you remember, it was a very cold winter. That was what happened to Napoleon when he attacked Moscow. It was a very cold winter, and he lost most of his troops. The same thing happened to the Germans. They were getting closer and closer to Moscow. The winter set in, and then the Russians started winning that battle. Well, in the spring, when the snows melted, this great big tin stockpile had turned to these were bars of white tin, had turned to powder, and underneath the snow, all they had left was tin oxide because it had oxidized and everything. I mean, it was still there, and you could remelt it and re-refine it, convert it back to the metal, but it wasn't very useful in the current state. So people were worried about what they call tin pest. It turns out that lead also prevents tin pests, so you really don't need the antimony for that, but you'll read a lot of times that that's what they put it in there for. Turns out arsenic and iron have to be kept below 200 to 500 parts per million for intermetallics. Bismuth can help wetting, just like antimony, because it will reduce the copper oxide. But the problem with bismuth nowadays, in a small amount of bismuth like that, it's not going to hurt things. But people are looking for things to get rid of the lead in solders. And a lot of people are looking at bismuth alloys. I would say 60% of the papers I see, people are looking at bismuth alloys to replace the lead alloys in solders. And the problem with that is recycling. A lot of this stuff is going to go in automobiles. And right now, we recycle about 70% of the iron in the world, the steel that we use. It turns out, if you get bismuth and iron, you turn it into junk, because the bismuth goes to the grain boundaries. It causes it, during hot rolling, to crumble apart. It embrittles it because you have this low melting bismuth at the grain boundaries, and you can't get rid of it. There is no way, once bismuth gets into iron, to refine it out. You would turn the iron back to iron oxide before you can get rid of the bismuth Okay, so some things you can get out of iron, like carbon or silicon or manganese and things, because they have oxides that are more stable, and you can burn out the oxides of these other things. But bismuth, tin, and a few other things, once they get into the steel, they will stay there. Tin's not terribly harmful. I mean, we use tin-coated steel for soup cans and things like that, and have been for years. But tin plate scrap is worth a lot less, about 25% less, because you have to dilute it with nice new stuff to keep the tin down to a low enough level that it's not harmful. Bismuth is harmful in steel at the 1 or 2 parts per million level. And so the only way you could, if you decided to put bismuth into solders, the only way you could recycle an automobile is if you rip out all the electronics before you recycle the car. And now the value of recycling that car, or the cost of recycling that car, makes it so expensive that you might start seeing cars go into landfills again. You've got a serious problem. So the idea of using bismuth as a replacement for lead tin solders kind of scares the people in the steel industry to death, because they know that people are just going to be destroying the scrap. Another example where impurities, a small amount of an impurity will really hurt things. I didn't tell you about the aluminum scrap in Tennessee, did I? We recycle a lot of aluminum cans and stuff, and it turns out one Alcoa plant in Tennessee was getting aluminum cans back from Mexico, and they found that whenever they remelted these aluminum cans, they were getting high lead contents, and it turns out aluminum and lead, you can't tolerate more than about 5 parts per million lead in aluminum before it destroys the aluminum, and it's just brittle and junk, and it has to go back to the smelter. So you haven't done a whole lot of recycling at that point. You can get the lead out of the aluminum, but you have to go back and do a refining operation. The steel, you got to take it back all the way back to the ore to get the bismuth out of steel. So they thought that what the problem was maybe the Mexicans were slugging the thing, because you basically buy the scrap by weight, and they thought they were throwing lead in there to as an impurity to increase the weight, and lead's cheap. cheaper than aluminum anyway. Turns out that's not what it was. They ended up tracking it down. In Mexico, they still have leaded gasoline, and they also don't have 5% deposits on their bottles, and so people just throw the cans along the side of the road. Some poor people come along, pick up the cans, and it turns out if you plot the lead content next to the highway in Mexico, so here's the highway, if you plot the lead content, it decreases for about 100 meters on either side. It's basically the pollution from the lead and the gasoline, and enough of it was falling on these cans by the side of the road to destroy the recycled aluminum. So their solution was to quit buying aluminum scrap from Mexico. I don't know what the Mexicans are doing with it. Cadmium, 10 parts per million. A lot of times people think that CAD-plated surface will be a good one to solder to. It's not, because a little bit cadmium impurity destroys things. Gold and copper, 800 parts per million. It causes intermetallics, and that's why you like to keep it out for the copper reason. For the gold, you don't ever want to see it get this high, because at that point, your solder is worth more than, or the gold in the solder is worth more than what you're soldering probably, so you want to send it back to the refinery anyway, so far as that goes. Nickel's rarely found, but it doesn't have any serious detrimental effects unless you get really, really high in nickel content, but they never get that high. Silver is often limited to 0.015%, but you actually can put in up to 2%. And the only reason you limit it to this is because it's valuable enough to go back to the refinery if you've got that much silver in there. And sulfur is a serious problem. 7 parts per million will destroy the solderability. Sulfur is a surface active element in coppers. On copper. It's actually surface active on most metals. And the copper sulfide is more stable with respect to the fluxes that are typically used in the copper oxide, and so it will inhibit the cleaning action and the wetting action and destroy your solderability. I remember this was the first LFM class, so this was about 1989 or 90, and we had a team at Digital Equipment, the company no longer exists, and at must have been Intel. Yeah, it's Cupertino, right? But they were one of the reasons Digital Equipment no longer exists is because of this project, which was to build the VAX 9000. That was back in the days when IBM was making $40 billion a year selling mainframe computers. And that was the heart and soul of the IBM business. And Digital had started out with the mini computers, and they wanted to go to the big mainframes because that was the only way they were going to grow beyond a $10 billion a year company, was to get into the mainframe business and start eating away at IBM's $40 billion market, which they had a near monopoly on. And so they were going to build the VAX 9000 computer. And the VAX 9000 used tab tapes, and you've seen tab tapes now, that they were going to, Intel was making a very special chip for them. The chip down in Arizona would go over, or would be bonded by Intel on these tab tapes that were just produced down the road in Arizona. And then that stuff would be shipped to Cupertino, California to make the outer lead bonds. So the inner lead bonds were going to be made at Intel, and the company making the tab tapes, which had a 200-step process for making those tab tapes. I told you those tab tapes had lots, well, I think I told you they had lots of layers. Turns out each one of those tab tapes is worth about $50. So those little pieces of junk I sent around to you, well, actually I sent around, actually, in years past I actually used to give those out because Intel gave me about 500 of them once, but I ran out of them this summer. But in any case, the tab tapes would be produced by Rogers Corporation, sent to Intel for the interlead bonds. That was okay. Then they got sent to Cupertino, and it might be a month later that they would get around to trying to solder the outer lead bonds on this tab tape. It turns out the solution they were plating the copper in was a sulfur-based solution, it was sulfuric acid. And when I heard that, I said, this is never going to work because a little bit of sulfur contamination on there is going to destroy the solderability. And sure enough, it never did work. The VAX 9000 was about a year and a half behind. By that time, microcomputers, which we now know as PCs, were getting powerful enough that you could network a bunch of those and essentially do a lot of what people were doing on mainframes anyway. So IBM lost the mainframe market and everything else. But in fact, it was a solderability problem, and the people weren't familiar with the fact that just a little bit of sulfur was going to degrade the solderability dramatically. Aside from the fact they did no special cleaning, and the whole problem here of cleaning, the copper surface degrades rapidly after cleaning. These guys were waiting a month and they were doing no special cleaning. And they couldn't use much of a flux because of the limitations about corrosion in the process. So it was a defective process concept from the beginning, and that's basically what happened to the VAX, one of the major things that happened to the VAX 9000. Okay, we'll see you tomorrow.